Hello everyone. In this session, I'd like to explain the motional electromotive force. The figures show the slit wire generators. So we solve the induced EMF by the slit wire generators. Epsilon is given by minus B velocity times L is the length of slit wires. The induced EMF can be explained with a Lorentz force. I'd like to explain. So in these situations, positive charge is moving to the right, following the motions of the slit wires, moving to the right. Then the magnetic field is directed to the board. Then if you take a scalar product, V cross B is become this direction. So positive charge is moving to upward directions. So positive charge is moving to the upward. Positive charge is moving upward. Then what's happened? Positive charge we expect is accumulated. Accumulation of the positive charge at the one end of the slit wires produce the electric field because the other end is lost the positive charge. So electric field is induced inside of this slit wire from the positive charges to the negative charges of the E. Potential difference. Then accumulation of the positive charge. So positive, as I explained, positive charges are accumulated in this end, and the negative charge is accumulated in the other end. So this produces the electric field in this direction. So because of this electric field is a positive charge, experience the electric force. Electric force is acting on this positive charge, and the magnitude of the electric force is expressed QE. Then positive charge is moving to the right because following the motion of the slit wires. Then also Lorentz force is acting. Magnitude of the Lorentz force is QV cross B. So magnitude is expressed QB B have to be equal to the QE. So from this equation, electric field, induced electric field inside of the slit wire is expressed as V times B. Velocity times the magnitude of the magnetic field. So this electric field we derived using just only the Lorentz force. Then potential difference is expressed E times L. L is the length of the slit wires. So you can substitute this E is here. Magnitude of the potential difference becomes the VBL. This expression is agree with this expression. Magnitude of the EMF is a BBL. BVL. So we have a same expression. This agree with the solution to the previous questions. Induced electric field. The induced EMF also occurs when there is a changing flux through a stationary conductors. So actually in this case is the wire doesn't move. So in this situation the coil doesn't move. Instead the magnetic field is changing. EMF is induced in a coil. EMF is induced in a loop by changing flux of magnetic flux through a stationary conductors. We can use the same equations. Epsilon induced EMF is equal to the negative d phi sub b over dt. And the electric field is induced even when the non-conductor is present. In the first case, we consider the coil. But also we could consider this red loop. So no conductor is present. Is like red loop in the figures. The electric fields take a scalar product EDL. It becomes an induced EMF. So these two have to be equal. Then we can express. We call it this is the Faraday's law. One of the fundamental equations in electromagnetism. Differential form of Faraday's law. So Faraday's law, integral form of the Faraday's law, this expression. Then we can express the phi sub b is a magnetic flux is expressed with the surface integrals. Magnetic flux is expressed this way. Surface integral of the magnetic field. So this is a integral form of the Faraday's laws. And also the left hand side, E.dl is expressed with the Stokes laws. So line integral to the surface integral. Surface integrals convert from the line integral to the surface integrals using the Stokes theorems. Then right hand side should be the equals because left hand side actually exactly equal. So from these equations we discovered S nabla cross E plus round B round T dot N ds equals 0. So we correct all the term into the left hand side. Then you can take any surface of the ds. But this equation has to be satisfied always. So this means inside of the parentheses have to become 0. Then we have a differential form of the Faraday's law. Del operator cross E. So this is equal to the curl E. Equal minus round B round T. This is a differential form of Faraday's laws. In today's lectures, I explained the electromagnetic induction. Electromagnetic induction was discovered by Michael Faraday, and electromagnetic induction expressed using the equations del cross E equal minus round B round T. This is a differential form of the Faraday's law. Okay, this is the end of the today's session.